Welcome students to this next session on industrial metallurgy. This is session number 40 and these are the contents that we'll cover in this particular session. So we'll start with again repeating that how do we do the classification of steels on a metallurgical basis. In the last session we had discussed the eutectoid reaction, and it was stated over there that classification of steels on a metallurgical basis is done with the help of the eutectoid reaction. And on the basis of this reaction, the steel which contains exactly 0.77 percentage of carbon in it is called the eutectoid steel. And some books would also refer this as 0.8 percentage carbon composition. But again, to be more specific, any steel which contains 0.77 percentage carbon and remaining 99.23 percentage iron, that steel is called a eutectoid steel. The next big question, what would be the room temperature microstructure of the steel? Uh, uh, Practically, the room temperature microstructure of a eutectoid steel will comprise of only perlite, as I have written at the bottom portion of this diagram. So eutectoid steel comprises of perlite only. And what is perlite? Perlite is a mixture of two phases which contains eutectoid ferrite and eutectoid cementite, essentially in the weight ratio of 8:1, where ferrite lamellas would be 8 times wide as compared to the cementite lamellas. And in this eutectoid mixture, both phases would be present in the lamellar form with alternate lamellas of ferrite and cementite. Okay, then we had gone on to say all steels to the right of this. That means all steels with carbon between 0.77 to 2.11 percentage carbon are called hypereutectoid steels. And these hypereutectoid steels, what would be their room temperature microstructure? Their room temperature microstructure would be perlite. See students, any iron carbon system at room temperature, if it has reached through equilibrium cooling, it will definitely contain perlite in it. We have to see what in addition to perlite, mind it, under equilibrium cooling conditions, because we are talking about iron carbon equilibrium diagram. Diagram means we have heated cooled a system under strict conditions of equilibrium, slow rates of heating, slow rates of cooling. Fine. So if we are talking about a hypereutectoid steel which has carbon anywhere between 0.77 to 2.11, then the steel's microstructure would consist of perlite, but along with that, some proeutectoid cementite would also be there. And similarly, if you are talking about a hypoeutectoid steel, any steel with carbon in the range 0.02 to 0.77, then that steel would have in its microstructure perlite, plus along with that there would be some proeutectoid ferrite. But if somebody asks you that in any of these steels, how many number of phases are there under room temperature conditions or just below the eutectoid temperature, you see phases are only two: ferrite plus cementite. Some of that ferrite plus cementite is perlite, and in case of hypoeutectoid steels, in addition to perlite, we have proeutectoid ferrite, and in case of hypereutectoid steels, in addition to that perlite, we have proeutectoid cementite, and in case of an exactly eutectoid steel, we only have ferrite and cementite, which all has come through the eutectoid reaction. So all ferrite is uh, eutectoid ferrite and all cementite is eutectoid cementite. So that brings us to the end of the classification of steels on the metallurgical basis. Now, another very important and interesting thing that we must know, that what is meant by a critical temperature and what is meant by a critical temperature line. So the heading is critical temperatures on the iron cementite equilibrium diagram. Students, any temperature for the iron carbon system which represents either a change in phase or represents a change in the magnetic properties of a phase is known as the critical temperature for iron carbon system. And these I again repeat, any temperature for the iron carbon systems or on the iron cementite diagram which either represents a change in phase taking place at it, or represents at least a change in the magnetic characteristics of an existing phase happening on it, such a temperature is called a critical temperature. And this critical temperatures are represented on the iron cementite diagram with the help of some lines which already are a part of the diagram, and there are a couple of lines which have been superimposed to represent the critical temperatures on the iron cementite diagram. And any such line or lines which represent or signify a critical temperature are called the critical temperature lines on the iron cementite diagram. We have six of them. Let me name them one by one. We have this A0 temperature, then we have this A1 temperature, A0 temperature or A0 temperature line, this blue line, dotted line, which has been specially superimposed, which otherwise is not a part of the iron cementite diagram, is called the A0 line or the A1 temperature. And this is the A1 line representing the A1 temperature. This KE is the A31, another A31 line representing the A31 temperature. Then we have this A2 line, this blue line that you can see over here. Then we have this A3 line, JK, and finally we have this KG line, which is ACM, CM for cementite. Now let us see what do these lines signify. Let's talk about them one by one. Students, first of all, A0. A0 is a isothermal line because the temperature is constant for all iron carbon alloys. It's a constant temperature of 210 degrees centigrade. If you remember, when we were discussing about the properties of cementite, we had said that till 210 cementite is partially magnetic, and beyond that it is totally non-magnetic. So A0 is the critical temperature of cementite, and this line is representing the A0 temperature. So this line is called the A0 line. And what is this A0 line? Signifies the critical temperature of cementite. If your iron carbon alloy is below this line, the cementite contained in it would be partially magnetic. But if you are having an iron carbon alloy above this temperature, above this line, and the microstructure of your material system contains some cementite, that cementite would be totally non-magnetic. Now we come to the next temperature, that is A1 line. A1 line or A1 temperature is again constant, and it is only defined for hypoeutectoid steels. I again repeat, any steel with up to 0.77% carbon is a hypoeutectoid steel. What does this steel signify? Students, when we'll discuss heat treatment, you'll see that in any heat treatment process, the first step and the foremost step is the formation of austenite in your steel, right? And in some heat treatment processes, the requirement would be that you just do not want some austenite, but 100% austenitic structure in the steel. So you'll always talk about temperatures, a lower critical temperature of steel, when austenite begins to form in the steel, and there would be another temperature called the upper critical temperature of the steel. Upper critical temperature of the steel would mean that if you go beyond that temperature for a steel, then the steel's microstructure would comprise of 100% austenite. Now this MK or 727 or A1 line is the lower critical temperature of hypoeutectoid steels. Means if in any hypoeutectoid steel you wish to state that at which temperature will austenite phase begin to appear in the steel, that is given by this line. So you take any hypoeutectoid steel, see that steel has got perlite and proeutectoid ferrite in it, right? Or in simple words, has got ferrite and cementite in it. So when you start heating any hypoeutectoid steel, but what is the first temperature when austenite will appear for the first time in your steel? That would be through the eutectoid reaction. And what happens in the eutectoid reaction during heating? See, during cooling, austenite becomes perlite. During heating, perlite would become austenite. So what is the room temperature microstructure of any hypoeutectoid steel? perlite plus pro-eutectoid ferrite. So as you heat a hypo-eutectoid steel and reach this temperature 727, entire perlite transforms to austenite, but we are still having some pro-eutectoid ferrite left. But what is the first temperature where you get to have austenite in the steel? It is 727. So this line is the lower critical temperature of hypoeutectoid steels, and the same is true for hypereutectoid steels. For hypereutectoid steels, hypereutectoid steels are from point K till point G composition. So what is the lower critical temperature of hypereutectoid steels? This line only. So for hypereutectoid steels or for cast irons, what is the minimum temperature? See, that is the same as was for hypoeutectoid steels. But see, this incidentally is a common temperature for hypoeutectoid steels and for hypereutectoid steels. But these two type of steels have got very different behavior, very other different critical temperatures. So right from the beginning, we'll talk about them separately, even if they have something, even if they have their lower critical temperatures at the same value, still we have designated them different, because right from the beginning we'll differentiate between these two type of steels and talk about their details very separately, differently. So if somebody asks you that what is this A31 temperature, you will say, sir, during heating, this is the minimum temperature where a hypereutectoid steel would show austenite present in it. So this is the lower critical temperature of steels. So this entire line is called A31. Okay, then this blue line over here is the A2 line. And what does this represent? Bacho 768, this represents the Curie temperature of ferrite phase. If you remember, when we had discussed ferrite phase in the class, its properties, etc., we had said the Curie temperature of ferrite is 768. Below 768, ferrite is totally magnetic, and after 768 it's totally non-magnetic. And why have I drawn this line only up to here? Why not beyond here? Because beyond this point you will never get to have ferrite in any steel at a temperature as good as 768. So whenever ferrite is present in hypoeutectoid steel below 768, it would always be magnetic. Beyond that it would be non-magnetic. And if ferrite is present in any cast iron or in any hypereutectoid steel, it's always going to be a ferromagnetic, that is magnetic in nature, because beyond 727 you don't get ferrite in hypereutectoid steel or a cast iron, and 727 is a temperature lower than the Curie temperature of ferrite. So whenever you get to see ferrite in them, ferrite would always be magnetic. But in a hypoeutectoid steel, if you cross 768, then ferrite would be seen, but it would be non-magnetic. Then students, we come to A3 temperature. See, A3 temperature is not a constant temperature for all hypoeutectoid steels. This is the upper critical temperature of hypoeutectoid steels, and this is that minimum temperature during heating which must be reached for any hypoeutectoid steel in order to get 100% austenitic structure in it. So you can see for yourself that it is this line beyond which every any hypoeutectoid steel must be present, so that you can see 100% austenitic structure in the steel. Similarly, students, this is the upper critical temperature of the hypereutectoid steels. So if you have to see steel in 100% austenitic structure in any hypereutectoid steel 0.77 to 2.11, you will at least have to come till this line. So this is the upper critical temperature of hypereutectoid steels. When we'll discuss this particular topic in the class live, then we will also discuss with you as to what are the reasons why this designation 0, 1, 1, 3 or 3, 1 or 3 or CM attached to these temperatures. So I hope you have understood what is meant by a critical temperature, what are the different critical temperature lines on the iron cementite diagram, and what is the significance of each of these lines. I enjoyed preparing this session for you, and I'm hopeful that you'll also enjoy whenever you'll watch this session. Thank you for being there. Thanks for watching.